So we're going to go over derivatives. And this is actually lesson 2.2. We went over 2.1 actually on Friday. Okay. So 2.2. We have a couple rules here, and they're discussing them. If we're finding a derivative of a function, this is in prime notation. The derivative of a constant, any value of a number, say k was 5, the derivative is just equal to the value of 0. Okay. Our power rule, if we have the derivative of a variable when n is the exponent, we bring the exponent down in front, multiply whatever coefficient was there by n, and the new exponent on top is 1 less than the one that was there before. This will make more sense when we go through an example of it. A constant multiple is pretty much the same thing I just spoke about here. We're finding derivative, you find the derivative of the variable, and you multiply whatever the exponent was by the constant in front. And the sum and difference rules, all you have to really know is how to derive each of the functions within the greater function. So, p at x, if f at x is made up of p at x plus q at x, we just derive p at x and we derive q at x. We keep the addition sign the exact same. And the exact same thing holds for the difference rule. We derive p at x and q at x, and we subtract. So nothing really changes. The major rule, or the major two to remember from this lesson, is that derivative of a constant is 0, and the power rule. From there, we can kind of go through everything else. So we have two examples below. The first example here, we've been given f at x. So we're going to use prime notation when going through things. So what that means is when I'm finding a derivative, I put a superscript of 1 above our f. So it looks almost like a power of 1. So this means the derivative of f at x is equal to, and the very first one is our power rule. We're going to take the value of 3 and bring it down in front of x. So we're left with 3x, and the new exponent is 3 subtract 1, power of 2. Okay. This is also a difference rule, so we keep the subtraction sign, and then we derive the second number in our function. We bring the 2 down, we'll have 2x, and it's technically to the power of 1, but it's not necessary for us to write that. So the derivative of x cubed minus x squared is 3x squared minus 2x. Okay. Our second function, we're actually going to turn this into an exponent. Okay. And a root turned into an exponent ends up being x to the power of a third. Okay. We're still going to use our power rule. We'll bring the third down, and technically there's a 1 in front. So 1 times 1/3 is 1/3. So we have 1/3 x. And then we have to subtract this value by 1, so which that means is 1 over 3 subtract 3 over 3 gives us negative 2 over 3 as our exponent. Usually we like to write our exponents as positive values. Okay. So this is going to work out to be 1 over 3, and then we can write it as the third root of x squared. And your third root there. Okay. So all I did was rewrite this question. This is essentially an answer, but if I wanted it as a positive valued exponent, this would be our final answer, a more simplified version. Our third example, we're going to talk about finding the slope of a tangent. When we derive something, we are finding the slope at a specific point in time. In other words, the rate of change. Okay, so if we have a curved line for a function, when we derive it, we've now set up an equation to find rates of change along this slope. We just have to plug in what our x values are, assuming that we are finding the variable x in reference to y. Okay? So in this example, we have our function f at x. Okay? And I'm going to actually simplify this function for myself before I get into solving it. I can rewrite it, actually, sorry. I want that to be positive. So I'm going to rewrite this as f at x is equal to x to the power of negative 5 when I go to solve it. They want us to find the slope of the tangent to our function when we have x at negative 1. Okay? They've given us the y value, but the value that is important for us is our x value, because we'll be subbing that into the derivative. So let's find f prime x is equal to, when we derive this, the negative 5 comes down in front. And when we subtract by 1, what will our new exponent be? Negative 6, that's right. Okay. I'm going to rewrite this again as a rational. We'll have negative 5 over x to the power of 6. So this is our f prime x, the derivative of our function. And they wanted us to solve for it when x was equal to negative 1, which means this equation, I'm going to plug the value of x is equal to negative 1 into it to see what we get. This will give us the slope of our tangent. So the slope of our tangent here is negative 5 over negative 1 to the power of 6. Anyone know what that would be? Which gives us what slope? Negative 5. So the slope of our tangent at this point is a value of 5. Now they might extend the question and tell you to find the equation of the tangent line, and you have the slope here. So you would just kind of plug that into y equals mx plus b, negative 5 being our m. You have the coordinates of negative 1 and negative 1. You plug those into your x and your y, and you can solve for b. I know I'm going through this very quickly. But think of it like this. Negative 1 is equal to negative 5 being our slope times negative 1, our x value, plus b, which gives us negative 1 minus 5 is equal to b, our b value being negative 6. So the slope of our tangent line would be y is equal to negative 5x minus 6. I know they didn't ask that, but we extended it a little farther. Okay.